Okay, let's start off with an example on the Doppler effect that we did last time. Let's do it together, then maybe I'll reflect later in the class. Okay, so we have a car and train are moving in the same direction. Okay. Okay, the car moves at 30 meters per second, and the train is faster, but it's behind the car. Okay, and the train is going 40 meters per second. Okay, if the train whistle has frequency, or let's say pitch, of 1,000 hertz, what pitch is heard by the car passengers as the train approaches? And then the second part, and as it passes ahead. Okay, so we'll take the speed of sound for this case to be 340 meters per second. All right, so we have car originally ahead of the train, they both went in the same direction, the train passes the car eventually. Okay. But I want to know what is the pitch of this 1,000 hertz train whistle as heard by the car before the train catches up and after the train passes. Okay. So let's first consider before. So we have, here's the train. Let me just draw it as a rectangle. Let's not get fancy with the train. And it's moving like this, and we have the car. Okay. And the car is going in the same direction. Okay, so now let's figure out who is the source. The source, the train is the thing with the whistle, so that will be the source. Okay, Vs, and then the observer is the car because the people in the car are the ones listening. All right, we're told that the car moves with a speed of 30 meters per second. Okay, so remember the convention I wrote down last time. Here's my notes. The convention was VO and VS are positive when they bring the source and observer closer together. So whenever it points towards the other, it's positive. If it points towards away from the other, it's negative. Okay, remember that. Okay, so we will just simply use this for the velocity of the observer. So this is the observer. Is it pointing towards or away? Yeah, it's pointing away from the train. So that means we're going to say it's negative 30 meters per second because it points away. All right, now the source is the train. Is it pointing towards or away? Yeah, it's pointing towards the car, so it's going to be positive 40 meters per second. Okay, so it points towards. Is everybody clear on that? Okay. Now the rest is pretty straightforward. Once you got this, you just say the frequency heard by the car passengers is the frequency of the train, the natural frequency of the train whistle, times the speed of sound, plus the velocity of the observer divided by the speed of sound minus the velocity of the source. So now we just plug in the values. We have 1,000 hertz for the natural frequency of the train whistle. And then we plug in the speed of sound is 340, so those V's without any subscripts are 340. The velocity of the observer, we said, is going to be minus 30, okay, on the top. And then we have minus what Vs is, so we have minus 40. Okay, any questions about that? Pretty straightforward? Okay. All right. Then we just plug in the numbers and we get 1,033 hertz. Okay, so it's a little bit higher than 1,000. Any questions about that? No. Yeah, question. Yeah, so it's approaching. So the train's going a bit faster. It's going to eventually overtake, but this is before it overtakes. Yeah, that's what I meant by before overtake. So maybe I should write that, approaching. Okay, let's say after. So this is as it passes. Passes ahead. In this case, the train is already ahead. And so then we have our car. And it's a little slower. Okay. And now we have, this is still the source. This is still the observer. Now the train is, right, which way is it going? Is it pointing towards or away? This way. Yeah, so it's negative, it's pointing away. So it's going to be negative, so 40 meters per second. And how about for the observer? Is it pointing towards or away? Towards, so it's positive. Okay. Does everybody get the hang of this? It's just, you see, which way is the arrow pointing? Say plus or minus. Okay. Now then, we say that the frequency heard by the passengers in the car is the natural frequency of the train whistle times V plus VO over V minus Vs. Okay. So then we have 1,000 hertz. And then we have $340 for the speed of sound. Then we add the velocity of the observer, that's plus 30. And then we have the speed of sound, 340, minus, and then Vs, there's another minus sign here, minus 40. Okay, so there's two negative signs there. All right, so then plug these into the calculator, and you end up getting 974 hertz. Yeah.
Is there so if it starts behind the car, you hear it, you hear it higher.
That's right.
And then once it passes it, you hear it lower.
That's right.
Is there like where you'll hear it gradually decrease? Because this doesn't really account for that if that's a thing.
Yeah. So what will happen is as it approaches, as it approaches, you hear it with a higher pitch, and no matter how far away the train is, because the speeds are constant, it will be the same pitch. Okay, and then after it passes, it will be lower. So it's just like it's at this tone, and it just jumps. It's like an instantaneous change. Yeah, exactly. Okay, very good question. Other questions? All right. Okay. So I had to download this. This is one of those downloads. The doctor told me the sound is kind of annoying on this thing. So it's like a high pitch what I'm going to do, I'll tell you now before I turn it on. I'm going to just spin it around. Okay, let me just make sure it's secure. It's secure. Here. I'll just spin it around like this. Right? So let's try this out. Do you hear a change in the pitch as it moves towards you and away from you? Okay, that's the Doppler effect. Okay, any questions about that? Usually when I do that, I clock myself on the head. I didn't do it that time. Okay, let's go on. Let's see. So, a couple of things I want to mention. I will start putting up stuff on our D2O webpage to get ready for the final exam. One of the things I will do is I'll go through. I will make a list of practice problems for the material beyond quiz 6. I will also try to clean up some stuff from the stuff in quiz 1, quiz 2. We didn't do reviews then, so I will record the reviews for those. And I'm going to make it such that you have all this. What you should have is you'll have a review for quiz 1, 2, 3, 4, 5, 6. We'll have the actual quiz with solutions. And you'll have the practice quiz with solutions for 1, 2, 3, 4, 6. And then you'll have some additional material for material beyond quiz 6. And some practice finals that that's clear enough. The other thing I want to mention is, somehow I forgot to do some of these. I like to post videos, and for some reason I didn't think of doing this earlier, but now let me catch up. So here are some interesting YouTube videos. This is, for example, I don't know how the sound's gonna. The sound's not going to really. That's unfortunate. How do I do the sound? Well, it would just, there's no sound on this video. Okay, so never mind. So this is a slow motion of a violin string being stroked with this bow. It's so slow you can't see it, but it's just starting. Notice how there's a pulse being sent down the string. You may notice, let me start it from the beginning again. So you'll notice that the pulse goes down on one side and it comes back on the other side. So it sort of does the circular thing. It goes down on one side and it comes back on the other side. See if you can notice that. The pulse goes down one side, it reflects and comes back the other side. You see that? We'll talk about that. When you fix a string on two ends, you send a pulse on one side, it flips over before it reflects back. And then eventually it just starts vibrating the string. This is what we'll be talking about today. Okay. And so let me, since it's, let's speed it up. So that's how the string gets vibrated. You'll notice actually that the other string starts to start vibrating as well. That's actually because it's resonating with the G. So this is the G string, this is the B string. There's actually a relationship between the frequencies. There's a 3-to-2 frequency relation. So this starts vibrating. Okay. The other thing I want to, well, I'll play the video after we talk about the physics behind it. Okay. Let's put this on. So we're going to talk about superposition. So sometimes people say, call this the superposition principle, so let me write that down. All right, so suppose I have a string and I have a little wave pulse here, and I have another wave pulse over here, make it a little bit bigger so you can distinguish the two. And let's say this one is moving in this direction, this one's moving in the opposite direction. They're heading towards each other. Now, a little time later, so a little time later, what you'll have is they will kind of be on top of each other. Right? This pulse is still going like that, this pulse is still going that way. Okay? And then eventually, even later, they will pass through each other. Okay, so at any given time, to find the displacement due to this wave, this pulse, you just simply add the displacements together. Okay, so the combination, well, let's see, how should I say it? The total wave is the sum of the two. That's the idea of superposition, meaning you just add them together. Everybody clear on that? Okay. All right, so we're now going to talk about some very simple cases where we add together waves. And so let me tell you some terms. So if I have two waves, I can talk about them being in phase, or what's called constructive interference. What that means is, suppose, for example, we were all reading some passage in some book. I don't know. Okay? If we all started at the same time, we'd be constructively interfering with each other. We'd be saying the same thing, and we'd be including the amplification of that. So this is sort of the same kind of idea. We have two waves that are doing the same thing. Maybe one wave is doing this, the other wave is doing this at the same time, so that they're constructively interfering with each other. Maybe you wouldn't use the word interfering, but in physics we still call it interfering. But it's constructively interfering, where they add up together. Okay. So let's, I'll show you what I mean. So suppose I have let's make a snapshot at t equals to 0. And let's say the snapshot of one wave with some amplitude a here. And then here's negative a. And it looks something like this. Here is x. So I'm just drawing the displacement. And suppose I have now another wave with also amplitude a. So it goes from minus a to from minus a to plus a. It also goes like this. Okay, now suppose I add these two together. I add these two waves together, sort of like the superposition I had over here, two waves overlapping each other. Then what I would get, it's probably not that surprising to you when you add these two together. I will get a wave that has an amplitude that's twice as big. So now I have it going from minus 2a to positive 2a, to positive 2a. Okay, so it's going to be a bigger wave like this. Everybody sees that, right? That's kind of easy, right? Everybody got that? So this is the case where we say they are in phase, they're doing the same thing together, or we say it's constructive interference. And so a very simple way of writing this down in terms of these functions of the displacement function is I would say that my displacement is going to be a sine kx minus omega t. Okay, that's for one wave, but then I have another one for the second wave, kx minus omega t. If I add them together, I just get twice what I had. Okay, 2a sine of kx minus omega t. Everybody's good with that? You're just doubling it. Okay? This is not exactly conceptually hard to see. Okay. All right, now, the more interesting case maybe is suppose they are out of phase, exactly out of phase. So again, we will have two waves, and we will say, okay, this is separate. So now we'll talk about the case when they are out of phase, or pi radians out of phase. By the way, pi radians, hopefully everybody's good with converting. So pi radians is equal to 180 degrees. Okay. All right. So let me draw a picture. Yeah. So I have a here minus a. And I'll draw the first one the same way as I did before. Here's x. Now the second one, so maybe I'll draw a little bit more to it this time so it's clear it keeps going. Okay, if I want it to be shifted by pi radians, what that means, so 2 pi is one full cycle, one circle. Okay. So if you just have a pi shift of the phase, it's halfway shifted. So this gets moved over, this wave gets moved over halfway. So it goes from here to there, okay? And so as a result, this guy gets moved over here. Okay? But it's a wave, it keeps going. So on this side, there's going to be this guy. Does that make sense to everybody? It's been shifted by pi. So if you want to try to link these together, this is this point, this is this point. Okay. So now if I add these two together, what do you think I'll get? Yeah, you see that? It's just going to give a big fat 0. Okay, you can't, it's hard to plot 0 because it's just right on the line here, but it's this, okay, it's 0. Okay, so in terms of writing down the wave, the displacement of the wave, the displacement will be, I have one wave, it's a sine of kx minus omega t. That's, let's say, this guy. The other one will be shifted by pi. So how do I shift by pi radians? What I do is I put this phase constant in. Remember, I can put this plus phi 0 at the end here. In this case, I have nothing, but what I can do is I can put a pi in for the second wave. So I have kx minus omega t plus pi radians, like that. Okay. Questions about this? Now, if I take a function, if I take any angle, take the sine of that angle, and I compare it to the sine of the angle plus pi, just like I've done here by shifting it by pi radians, I end up getting the negative of the sine of the original angle. Okay. So what I'm saying is, when I shift this by pi, I end up getting minus a sine kx minus omega t. This is just how sine works. You see it right here. If I shift by pi either way, I get the negative of that sine function. Any questions about this? Everybody good with that? Okay, so then that's why it ends up to 0. All right, now what I'm going to do is I'm going to write down some So how many of you have seen the addition formulas for sines and cosines, like the sine of a plus b, or the cosine of a plus b, cosine minus? Yeah. Probably some of you have seen it, but it was not that interesting, so you may not even remember it. Okay. But I'm going to write down a formula that uses one of these what are called addition formulas. You don't need to remember. I'm just going to show you how we're going to use this here. So if I have some displacement, that was the out of phase case. Let me just show you the general case. Here's the general case. So if I have a displacement as a sine of kx minus omega t plus a sine of kx minus omega t plus phi. Okay. Using some of these sine addition formulas, or cosine, well, sine addition formula is enough. You end up getting, I'll just give you the result without deriving any of it. It's going to be 2a cosine of phi divided by 2 times the sine of kx minus omega t plus phi over 2. Okay. So if I just stare at this for a second, this is the thing out in front of the sine function. So this ends up being the amplitude of the wave. Okay, the thing to notice is that when the phase difference between these, remember we were talking about phase differences, we talked about phase of the wave, that's what's inside the sine function here. What's inside the sine function here has this extra phi. So the phase difference between these two is just this extra piece phi here. Okay? So notice that that is what determines the amplitude of the wave. If phi is equal to 0, if phi is equal to 0, that means they're in phase. And then we have the cosine of 0 over 2 is going to be 1. Okay? So that's why 2a cosine omega over 2 in that case will be equal to 2a. But if phi is equal to pi radians, and these are out of phase, and we get 2a cosine of phi over 2. Let's plug that in. So cosine of pi over 2 is 90 degrees. So the cosine of 90 degrees ends up being 0. So that's why when you're out of phase, you get nothing. Does that make sense, everybody? Okay. So this is just a general formula. If you're halfway in between, you get a little bit in between. Okay. Everybody following that? All right. You don't have to remember this formula at all. So I'm just trying to show you how this works with math. Okay. The next thing we're going to talk about is reflection. So as you saw with the video with the violin string, when you have a little pulse, and the pulse comes down and it hits the boundary, it comes from one side and then it flips over the other side before it reflects back. It goes down on one side and it flips over. Let me try to draw that with this sheet of paper. So this is reflection. Okay, so we're going to consider the case where we have a fixed end. So let's say we have an incident pulse like this, and let's say it's tied to some wall. This is a wall just tied some way. Okay, and it's fixed. So this does not move. And if this is the incident pulse coming in, okay, and sometime later, it's going to be right at the wall boundary here. It's just approaching, it's touching the wall now. Okay. Now, what happens is at this position, what's going on is there's some string tension here, and there's this big kink right at the wall. Okay, so the string is trying to pull up on the wall, but the wall's not going to move. So as a result, what's happening is that from the point of view of the string, the wall is trying to pull the string down. Does that make sense? Because it's pointing, the wall is trying to actually pull this string down as it gets right to the edge. As a result, what happens is that right afterwards, it actually flips over. It flips over. Here's the wall. Okay? And it flips over, and then it starts going the other way. Okay? And then you have the pulse going the other direction. That's what we saw with that violin string. It just flips over like that. It sort of does a little circle. Okay? Any questions about that? If you don't believe it, you find some little string, something, and just tweak it and see how it flex off the boundary. Okay, the next thing we're going to talk about are standing waves, which are kind of interesting. Okay, so the idea of standing waves are waves that are not moving, they're not pulses. Rather, they go up and down, sort of like the violin string starts vibrating back and forth like this. Okay, so let's consider two waves like this, where I have a sine of kx minus omega t. Now let's take a step back, where k and omega are both positive. Do you remember this traveling wave? Which direction is this wave moving in? Is it moving in the positive x direction or the negative x direction? Do you remember that? Yeah, it moves in the positive direction. It's kind of funny. With the minus sign here, it moves in the positive x direction. But now we can have another wave that's going in the negative x direction. It's actually kx plus omega t. All right, so if I have two waves that are moving in opposite directions, like this, when you add them together, you end up getting something kind of interesting. And so I'll just do it with math. Again, this is what I'm going to write down follows from the sine and cosine addition formulas, but maybe you're not familiar with those yet, but just realize there is a video that shows this with a simulation. Maybe I'll try to dig that up for next time. If I add these two together, okay, I end up getting 2 times a times the sine of kx times the cosine of omega t. Okay. Now, this may look similar to what we had before, but it's actually completely different. This is not a traveling wave, this is a standing wave, and let me try to show you why. So let's first take let's draw what this looks like when t equals to 0. When t is equal to 0, the cosine of omega t is equal to 1. And so it looks like, okay, I'm just drawing 0 for the moment. And it looks like the sine kx times 2a. Okay, so this is t equals to 0. Now, if I take a slightly different time, let's say a slightly small positive time, then this cosine will no longer be 1, but it'll be maybe 0.8 or something like that. So then I'll have 2a times 0.8 times sine of kx, so then it'll be a little smaller like this. Okay. Let's take t a little bit further. Maybe it'll be, cosine will then be 0.2 or something. So now it looks more like this. Now, at some point, cosine will pass through 0 when omega t is equal to pi over 2. So then I get 0. And then after that, the cosine will be negative. Then I'll have something negative times sine of kx, so they'll be like this. All right, so then I will start getting things as a function of time that look like this. Oops. All right, I get sort of this shape. Questions about that? So these are just vibrating, these are what are called standing waves. This is a standing wave. There's no sense in which it's moving anywhere, it just goes up and down like this. Any questions about this at all? Okay, let me tell you some terminology. These points here, these points where things do not move, they are called nodes. N-O-D-E-S, nodes. This is a node, this is a node, this is a node. Okay. Halfway in between the nodes are the places where we have maxima, or a very weird term, they're sometimes called antinodes. Okay? So maximum because that's where the displacements are maximized. So you can call them antinodes because it's sort of the opposite of a node. Okay. Any questions about this? Yeah. So the thing is, because they're oscillating at different times, at one point it's a minimum, but then later on it's a maximum. So we just call them antinodes and maximum in absolute value. Okay. All right, so let's try to figure out what's going on. If I have the sine of kx and I set them equal to 0, the nodes occur when sine of kx is equal to 0. This is where the nodes are. Okay. And if I want to know what values of x I get for the nodes, I just see when is the sine function equal to 0. The sine function equals to 0 at angle 0. It's equal to 0 at angle pi, at 2 pi. So if I'm solving for x, I get kx is equal to 0, or I get pi, or 2 pi, etc. like this. Does that make sense, everybody? Okay. Now, how about the antinodes? The antinodes occur when the sine, so let me separate this out, when the sine of kx is equal to plus 1 or minus 1. Okay. That's how we get either 1 or minus 1. And so that means that kx is equal to halfway in between these nodes. So it would be pi over 2, 3 halves pi over 2, 5 halves pi over 2, and so on. So just halfway in between 0 and pi is pi over 2. Halfway between pi and 2 pi is 1.5 pi, or 3 halves pi, and so on. Any questions about this? All right. Now, let's see. I don't have quite enough time to introduce the standing waves on a string, but I have enough time to show you the video that it goes with.